Welcome back. We're now ready to introduce strong induction. This proof technique is also used to prove the same kind of theorems that we proved with mathematical induction, namely theorems of the form for all n greater than a, p of n is true, where a is an integer. So what is strong induction? Well, it's an inference rule similar to the one for mathematical induction, which allows us to prove theorems of this form. But the advantage of strong induction over mathematical induction is that it sometimes makes it easier to write the proof. So I will illustrate that in the next example, but for now let's focus on the inference rule itself. And I will start with the second premise, since this is really the heart of induction in general. Remember, the second premise says that from p of k is true, you can infer p of k plus 1, where k is an arbitrary integer greater than or equal to a, which is the constant used in the theorem here. So what mathematical induction was all about is to prove that p holds for this integer by only assuming that p holds for the previous integer. Now, sometimes writing such proofs is kind of hard. And in particular, it's sometimes easier to prove the property for a particular integer using not just the property for the previous integer, but also for the one before that. So in other words, sometimes it's easier if you know that p is true for these two integers to infer it that it's true for the next one. And if you're going to assume p for two previous integers, sometimes it makes it even easier to assume for three of them, or for an arbitrary number of them. So notice, if we assume that p of k is true, and p of k minus 1, and p of k minus 2, p of k minus b, basically we are assuming that p is true for b plus 1 consecutive integers. And if from that assumption we can prove that p is true for the next integer, then we have the second premise of the strong induction inference rule. So the main difference between this kind of induction and mathematical induction is that here we use a stronger hypothesis. Notice this is the conjunction of b plus 1 propositions. So it's a stronger hypothesis than just p of k, which is used in mathematical induction. That's the reason why this inference rule is called a strong induction. Now let's look at the first premise. Remember, the initial premise in mathematical induction is to assume that the property p is true at least for the first element in the set p of a. Now in this case, this is not going to be enough. Notice we are assuming here that we have b plus 1 propositions that are true for b plus 1 consecutive integers. So to kickstart the induction, it's not enough to assume just one proposition, but we must assume that p holds for the first b plus 1 integer starting at a. So we must prove for the basis step not just p of a, but also p of a plus 1 and p of b a plus 2, etc., all the way to p of a plus b. Again, you have b plus 1 propositions here, you have b plus 1 propositions there, and these are the two premises we need for strong induction. Now, before we finish writing this inference rule, let's make sure we understand all of the variables that appear in it, namely the a, the b, and the k. So first of all, a, you don't have a choice as to its value. A is part of the statement of the theorem here. So that's an integer constant. You don't get to choose when you write the proof. Now, what is b in this proof technique? Well, b is any non-negative integer. In particular, notice what happens when b is equal to 0. If b is equal to 0, then a plus b is a, which means the premise here boils down to just p of a, like the first premise in mathematical induction. And if b is equal to 0, then you need p of k in the hypothesis in the second premise, and then you don't need any of the previous term because k minus b or minus 0 is also k. So again, if B is equal to 0, this second premise boils down to the same one as mathematical induction. So in a way, mathematical induction is a special case of strong induction when B is equal to 0. That's the first observation. Now, how about when B is greater than 0? Well, you are the one to decide what the value of B is when you write the proof. What do I mean by that? What I mean is that you're the one to prove that P of k plus 1 is true, assuming the inductive hypothesis. So it depends how far back you need to go before k, how strong the assumption you need to have to be able to prove P of k plus 1. If you can prove it with only P of k, then B equal to 0, and you're back to mathematical induction. But if it makes the proof easier to assume P of k and P of k minus 1, then you can choose B to be 1. If that's not enough, or it's still too hard, then maybe you can choose B equal to 2. See, you get to choose the value of B, and when you do that, that means you can change the inductive hypothesis, but you also need to change the first premise of the strong induction inference rule. So that hopefully clarifies the meaning of A and the meaning of B. Now let's turn our attention to the variable k in the inference rule. And for that, let's use a concrete example. Let's say A is equal to 3. So we have a theorem that says for n greater than or equal to 3, P of n is true, whatever P is. So you start writing the proof and you realize that the value of B equals to 1 makes the proof easier for you to write. So what does that mean? Well, first you're going to have to prove the basis step, which is going to be P of A, that is P of 3, and P of A plus 1, ... all the way to P of A plus B. Now, A plus B here is going to be A plus 1. So you're going to stop here. A plus 1 is 4, so the second premise is P of 3 and P of 4. So one thing to notice about B is that the number of propositions in the first premise is always one more than the value of B, since you start at A and you go all the way to A plus B. So here B is equal to 1, so we have 2 propositions here. And same thing here, in the inductive hypothesis, we're going to have B plus 1 propositions. So what are they going to be? Well, they're going to be P of k minus 1, all the way down to P of k minus B, but here B is 1, so we're going to stop at this one. So P of k minus 1 and P of k together should be enough to imply P of k plus 1. Now what I want you to think about is what is the smallest possible value of k, because k is an arbitrary integer. But what is the smallest possible value of k for which this needs to hold? Well, we already know that k must be greater than or equal to a because the theorem only applies to n greater than or equal to a. But I want you to pause the video now and to try and figure out what is the correct minimum value for k. Is it really a? So what is the smallest value of k for which this conditional is going to hold? Well, let's assume that value is 3. In particular, if k is equal to 3, then we would be trying to prove P of 4, assuming only P of 3 and P of 2. But there's a problem here because P of 2 may not even be true since the theorem states that P is only true starting at 3. So you see that it's not enough for k to be greater than or equal to a. The condition on k must be stronger. So how do we determine the minimum value of k? Well, we look at the general form here. What must be the case is that k minus b must be greater than or equal to a. In other words, k must be greater than a plus b. So in this case, k would have to be greater than 3 plus 1, that is 4. So let's check that. If k is equal to 4, which is the smallest possible value we would accept in this second premise here, we would be proving P of 5 based on the assumption of P of 4 and P of 3. And that works perfectly since 3 is the smallest value for which the theorem says P holds. So let me erase this example for now and modify our second premise here for the inference rule. Notice what we just argued for is that it's not enough for k to be an arbitrary integer greater than a. It must be an integer greater than or equal to a plus b. And this is the final form of the second premise for our inference rule. So after this long explanation, we have a full specification of the first premise, full specification of the second premise. Now what's the conclusion of this inference rule? Well, it's the theorem we were trying to prove in the first place. For all n greater than or equal to a, P of n holds. And that is the inference rule called strong induction. So make sure that you're comfortable with the form of this inference rule. It's a little bit more complicated than mathematical induction. In fact, it's a generalization of mathematical induction because, again, if b is equal to 0, this rule becomes mathematical induction. This is called strong induction because when you're writing the proof, you can make a stronger inductive hypothesis here to prove P of k plus 1. Now remember, this new inference rule is not more powerful than mathematical induction. In fact, it allows you to prove exactly the same theorems. But, as we'll show in a couple examples later on, it might make the proof a little bit easier. So how do we use this inference rule to write proofs by strong induction on n? Well, as before, we have to write two subproofs. First comes the basis step, which is to prove this conjunction. Remember that you get to choose the value of b, the value that makes your proof easier to write. Then the second subproof is called, as before, the inductive step. It requires you to prove this conditional for an arbitrary value of k, where k is an integer greater than or equal to a plus b. So when you choose the value of b, notice what happens. The larger the value of b, the stronger the hypothesis of the conditional is, and presumably the easier the proof will be to write, because you have a stronger set of propositions or bigger set of propositions to start from. But also if b is larger, that means this conjunction here is going to be bigger, and so you're going to have to do a little bit more work in the basis step. So once you have chosen b, here is the hypothesis that you start the inductive step with, and again this hypothesis is called the inductive hypothesis. So in the inductive step, you start with the inductive hypothesis, which you assume to be true, and from that alone you must be able to prove P of k plus 1. Once you proved both the basis step and the inductive step, then you have completed the proof of this theorem by strong induction on n.